Hello. In this problem, it is given that we have two concentric hollow spheres. Charge Q is distributed over them in such a way that the surface charge densities are equal. We are asked to find the potential at the common center. Okay. Okay, so here I have drawn two spherical shells. Uh, the radius, okay, so 1 second. Okay, so the radius of the inner shell is R and the outer shell is capital R. Okay, so this charge Q is distributed between them. Okay, so the distribution is assumed uniform on each shell. So let's say the charge on the inner shell is Q1, the charge on the outer shell is Q2. Okay, so here they're saying Q1 plus Q2 is Q. Okay, so this distribution is done in such a way that their surface densities are equal. Okay, so if I take the surface charge density of the inner sphere, how do I get? It is just charge divided by its surface area, which is 4 pi r square. And then how do I get the surface charge density for the outer sphere? It is Q2 by its surface area, which is 4 pi capital R square. So these two are equal. So that means the ratio of the charges Q1 by Q2 is small r square by capital R square. So we're dividing in this ratio and the total is Q. So that means immediately Q1 will be R square divided by R square plus capital R square into Q. So I'm assuming you can substitute and then substitute the value of Q2 and that Q1, or you can directly write like this. And then Q2 is capital R square by R square plus capital R square Q. So a lot of dogs barking early in the morning. Okay, so I think let's ignore the barking of dogs. Okay, so we have these charges Q1 and Q2. Now, how do I find the potential at the common center? Now, what do we know about potential due to a shell? Okay, so I think I've put a video which you can watch. Uh, the potential at any potential at a point just outside the shell, whatever potential you have, it's the same potential anywhere inside the shell. Because inside the shell, the electric field is zero. So that means when you're moving a charge inside the shell, the work done is zero. Okay, so because the work done is zero, the potential energy should not change, hence the potential should not change. Okay, so whatever potential the shell has at a point outside the shell, anywhere inside you should have the same potential. The same thing for the outer shell also. So whatever potential the outer shell creates at a point just outside the shell, you should have the same potential anywhere inside. Okay, so with this in mind, we can say the potential at C is created by potential by Q1 due to Q1, charge Q1, plus potential due to Q2. Okay, so what is the potential due to Q1? It is 1 by 4 pi epsilon naught. So whatever potential the shell has at a point just outside it will be the potential at the center as well. So we can write Q1 by R square. And how about the potential due to Q2? So whatever potential Q2 generates at a point outside it, you'll have the same potential at the center as well, at the common center. So it is 1 by 4 pi epsilon naught Q by capital R. Okay, I made a small mistake. I think I have written the electric field here. Just Be careful, this is not square, just r. Okay. So now let us substitute these values q1 and q2. So let's pull the constants out. So 1 by 4 pi epsilon naught. Okay, so here I think q by r square plus capital R square is constant. So I'm going to pull that out. So q by r square plus capital R square. And then what do I have in the first term? It is simply r square by small r. So I'll have r. And in the second term I have capital R square by capital R. So I'll have capital R. So that should be the potential at the common center.